Hello, everyone. Today we will be reacting to the latest Alan Becker video, Animation versus Math. We will be having today with us Muhammad Mohsen, the owner of the YouTube channel this video will be uploaded to, Karim Ibrahim, and me, Muhammad Rashad. The reaction will be genuine, will be simple, and we'll also have some interesting insights in math. I hope you enjoy it.
I think you might want to remove the word simple because what about to happen is not
we
gonna
will
be
try.
simple.
We will try to make it
Okay.
simple. We will try to make it simple.
It is not simple at all.
Mohsen is
The most of the video will be simple though, but there are like, 2 or 3 instances where, the
we have
animator of Alan
hard.
Becker really went over the roof. This is gonna be interesting. I'm excited for this.
Great. Me and Karim will be the viewer's point of view. Mohsen will be the experienced one in math. So we'll try to ask him the questions that maybe will get in maybe will be in your heads. I hope you enjoy the video and let's start.
And
What do you think?
if anyone has any questions, you can ask in the comments.
Yes.
Like we'll be responding.
Okay.
Okay. Without further ado, let's get right into it. So wait, can you guys can hear the voice, right?
Yes.
Yeah,
I can hear.
yeah.
Okay. That's nice.
One second. Can you pause it for 1 second?
Yeah.
I think we need to put some context to what's happening.
I think the stickman is just basically fiddling with addition
I
and
mean,
equal
why
operators.
he's here? Why he's here? What he's trying to do? He's trying to return to his home.
I don't
for the
think
original videos animation.
I don't think I don't think we know anything now. He didn't provide any context. He's basically existing here, and the video is going.
He's just
he just
playing
figured out.
with the numbers.
Yes, yeah, he just figured out that there are numbers. There is plus, there is equals, and he's just figuring out what they do. What does equal do?
He
Equal
just
here is
learned some math.
yes.
Math.
Equal here is basically playing the role of the calculator. Like he just presses the equal to evaluate. It just evaluates answers.
Like calculator. Yeah. Yes.
Yeah. And he's just playing with the symbols and numbers.
Now I think we need to pause here.
Yeah. This is the first.
All the previous. Anyone.
Everyone can know. Yeah, this is the first instance of something interesting in the video.
Do you want to give some insights?
It's basically the Euler identity. Like
first we have
the Euler formula. The Euler formula is written in this form. Hold on. Equals cosine theta plus I sine theta. It's basically a conversion between the Cartesian form of a complex number and the polar form.
Yeah.
And why is the -1? give us
y the minus 1, you just plug in pi. You just plug in pi here, which is called the Euler identity. It's very famous. It's actually
Okay.
usually written in this form. I pi plus 1 equals 0. And here you just put pi. Cosine of pi is minus 1. And sine of pi is 0.
0.
Just
Gives
gives
you
you
minus 1.
minus 1. Yes.
This is a
Okay.
famous equation of Euler, correct?
Yes. You can go to Google and just type Euler identity. You'll just get this right away.
Okay.
Okay.
Um,
Let's anything else?
let's continue.
Let's continue. This is where the fun part. This is the fun part.
Yeah.
Now, what happened here?
He just jumped
Yeah.
into
Explain.
the imaginary dimension.
Yep.
Yes. Why
So,
did it work? Why didn't it work now?
Right now, what didn't work?
-1 in the previous part, turn to E.
Yeah, I think it's just a plot.
Just a plot.
Yeah,
Just
if
No,
yeah,
no mathematical meaning or something.
yeah, we just need to, make something interesting. Like he's not just making a math video, he's making something that's supposed to be, it has some
Fun.
drama, it looks, it's interesting, right? So this is basically plot. So what he's gonna do right now, I think what he's trying to do right now is trying to figure out a way to bring it back. So
Okay.
he's doing some problem solving now.
Hey.
Yeah, hold on.
This is cool.
This is
cool.
yes, this is the definition of multiplication.
Yep.
Like if you go back to multiplication, like if you want to multiply, hold on, where's the drawing? Yeah, if you want to multiply 3 by 4, this basically means you add 3 4 times or you add 4 3 times.
He had it 4 3 times.
Okay. So in order to count the 3, you add 1 3 times. So you can say I'm gonna add 1 plus 1 plus 1, and then I'm gonna add this 4 times. So you're just gonna repeat it here again 4 times, okay? And one here and another one there. So it works this way, and it also works that way.
Yep.
There's also one extra insight behind this. That if you remember the formula for the area of a rectangle. Like when you want to arrive at the formula of an area of a rectangle, you basically say if I have a rectangle, and let's just assume for now that the sides are integers, okay? And you have here first you define the like a square of a unit area. You say here I'm gonna have a square. This square, this is
one
doesn't look like a square, but this is a unit area, okay?
Yep.
So you define the unit area, and you say this is 1, and you define the area is how many of these are inside this shape. Okay, how many units are inside? So if you keep going this way, you get another 1, and then another 1, and then you get here 4 of
another
these.
Another column.
Yeah, exactly. So adding these unit areas, this will give you the area. It's exactly this picture, but there is no, squares. It's just written in an abstract way. So if this was a rectangle of a height 3 and a base 4, then the area would be 3 times 4. Okay?
That's an interesting insight.
Let's keep going, because actually, this is an interesting insight, because we're going to need this in a while.
Okay, let's continue.
Yeah, here what he's trying to imply is that division, like the definition of division, if you want to divide an integer by another integer and it's divisible by it, like in this case, 2 divides 6. So you can divide 6 by 2. So what he's saying is that you keep subtracting 2 until you get to 0, and the number of 2's like the number of 2's that you subtract is the answer. In this case, it's 3. So this like kind of semi-transparent 0 right there is the number of times you have subtracted 2. So if you keep going, you subtracted 1, it gives you 1. This is the counter, right?
Mm.
Go again and then again. So this becomes the answer and it drops in place of 0 here.
Now, I think we need to pause here.
Yeah. This
think
it looks really cool.
We get undefined when we divide.
Yeah. It's the like if you use the same intuition, you say how many zeros do I need to subtract from 6 to get it to 0? And
Now,
you
infinity.
would actually never get to it. So it's basically infinitely many zeros.
Correct.
Okay, so there's like a catch with this explanation, because when you divide 6, like if we come right here, this actually we're getting into calculus here. When you try to divide 6 by 0, like here, you would usually try to explain this in terms of a limit. You'd say that this is the limit of 6 over x, for example, as x goes to 0. But there is just one slight problem here. This limit is actually not infinite. It's not infinity, because if you approach from below, you get a very small number here, but it's negative. So actually from below, like when you're approaching this from below, it gets you negative infinity. Like if you have this here, and this is the 0, when you approach it from below, you get negative infinity. When you approach from above, you get positive infinity, right?
Yep.
So you're only...
not about infinity, it's undefined.
Yeah, this is why we say it's undefined. In this sense, you can say this, like you usually can say this when you're dealing with radius or something which you know is positive. Like if this was like the limit as r goes to 0 of 6 over r, and we know that this r means radius, then you can say this is infinity. Because now it's a one-sided limit.
Okay.
Because there's no r.
There is no lower limit. There is no lower limit. This limit is actually equal to the limit
to define the r
from above. R is just something which is positive, basically.
Yes.
Like
yes.
it cannot go below 0. In x, we're assuming that it can go negative or positive. In this way, you cannot actually...
It's undefined. The other one is infinite.
Yes. Yes. But the intuition is still very good, though. Yeah, you would notice there's something to notice here. As you'd see, like there is an implicit meaning that you should get when you watch this. He's using the division sign, like the regular division sign, as like something which divides, but also provides insight into what is happening inside the process. But he's using the slash as a way of...
to hide this.
Yeah, as a way of showing the division, but not showing what's happening inside. Because if you go back here, you'd see
the final result.
Yeah. He just puts the slash and it gives you the final result, and then he turns it into the division sign and it gives you whatever is happening inside, which is a very nice touch. Okay, we go here.
He's still trying to find an Euler identity.
Yeah, he's trying to find the e to the I pi.
Yeah.
Now we get into the squares.
Yep.
Bro, that is so sick.
We need to pause here.
Oh, bro, this looks so good. This is amazing. Wow. Okay, so here we're using the same idea that we used before. That multiplication gives you the area of a rectangle, right?
Yeah.
But now it's a square. It shows you a square here. So you can imagine that each of these ones is actually a square of unit area, right?
That's a square. Yeah, correct. Square.
Yeah, it is a square because he's squaring.
Yeah.
Like this is why
Yes,
we call it squaring because it's square. Okay.
Yeah.
Okay. Now you're cubing, so he makes a cube. This
Yeah.
shows you the
Mm.
exact same definition of area, but now it's volume. And instead of you splitting your shape into squares of unit area, now you're splitting it into cubes of unit volume. And these ones act as these cubes of unit volume. And you add them all up and you get your volume here, right?
Yeah.
And then he moves into the fourth dimension. And here we have a tesseract.
That's a
Which
4D square.
yeah, exactly. It's like they call it the 4 cube. Like whenever you move higher in dimensions and you say I have n dimensional cube, we call it the n cube.
Yeah.
So this is a tesseract, and obviously this is not really a tesseract, it's a projection of it. And by the way, if we come here, that's not even a cube. This is a projection of a cube because we're looking at the cube
2D.
through
Yes.
a 2D, yes, through a 2D perspective.
Yeah.
Because you cannot actually visualize something in 4 dimensions. All you can is look at 2D projections.
But man, this is so
And
That-
then-
that's a 5D.
That's amazing. Now you move into the penteract, which is basically a 5 cube. And it looks so fucking badass.
Yeah, this is so sick, man.
1024.
We're back to the 4. Now he flips it. Bro, this animation is so smooth. Look at this scene. Look. Wow.
Now we go into the roots. Yes.
Yes. Now
Roots,
we can get where we want.
Wow.
This is a irrational number. This is irrational number.
Oh yes. The number goes to it goes to
This is
infinity,
irrational.
and there is no
We go
pattern
from-
in here.
We go rational, then
Now it's irrational, which is the square root of 2, and then
before irrational, we get what's called
yeah, you get rational and then
the
integers.
visit.
Natural numbers,
Natural numbers are the first.
Yes, so then rationals.
rational,
Second
irrationals, then
Yeah.
reals.
Correct.
Then he, of course, like you don't even need to continue the video to know this. He's gonna run into square roots of negative numbers, and this is where he's going to find the I.
Yes. Here we go to imaginary.
Yes. Get 2I.
Welcome, baby.
Welcome back. Now the fun begins.
Now, wait a minute. Why did this work? Why did this work?
Because he wanted to go to an imaginary dimension by I again, but when he threw an I, the multiplication
Is
of
the
2I
multiplication
gives you a
negative?
-1. Yes, which is real. So he just gets transported back to his dimension.
But in the reverse mood. So he entered this way and he got out this other way.
Hold on.
The other way, correct? Because it's negative now.
In this, it did. I don't actually see how it works in the animation.
I'm saying he
Look.
wanted to go to the imaginary. Then
Here's what happened. He first used I to open the dimension, and then the
Correct.
other I hit him, which opened the dimension again from inside, which spit him outside. But he was just, he was just rolling.
it was
so
an inverse.
we
it's
didn't
an
actually we didn't actually see the flip. But here he gets the minus. Oh yeah,
Yes, wait a second.
He used the Euler formula we talked about before.
Yes, the cosine and sine.
Yes, this is the one we were talking about before. Okay.
Yeah.
Use bias, yes.
But there is something here. There's a minus, like there's a minus behind. But then when it expanded, the minus didn't distribute.
Yes, it's cosine minus I sine.
Yeah, it was supposed to be 2 minuses, but again, you cannot blame for this because sine pi is 0 anyway. So whether it's plus or minus, it doesn't matter. It's still -1, right?
Yes.
Yeah.
Okay. So you gotta
mathematically correct in the end.
yeah. So it's still mathematically correct. Okay. And now, yeah. Now,
This one is cool. This one is cool.
Yeah.
The minus sign.
He
flips
inverts
him.
it.
Yeah, the
Reverse
minus
it.
sign flips him. Oh yeah. Okay.
No, wait.
Subtract pi and add
So
another
yeah,
pi.
he added. Oh my god, why can't I hit this right?
Make it
Yes,
make it slower. Make the video slower in this
He
part.
adds. Okay, I can use the mouse. He subtracted another I. Now this is e to the I0, which is 1, and then look, he rotates for a pi, which brings him back to e to the I pi.
Pi is 180 degrees, just for those who don't know.
Yes, pi is 180 degrees. So in order for him to rotate the
So
vector by
half
pi,
a circle, he moved half a circle. Yeah.
yes, you actually it's the same as multiplying by -1, which using Euler's identity is the same as multiplying by e to the I pi. This is why he got the e to the I pi back.
Mm.
Yeah.
Okay.
He moved them around 80, so he
Yeah,
got back.
yes. Now he uses the multiplication sign.
He
Multiplies
beats
speed.
himself.
This scene, remember?
And now it's time to do. Oh yeah.
Yeah.
I don't really
Minus
know,
1 plus 1 equals 0, so this is why
it
that's
is,
how 0.
but it is, but I don't really know what the 0 means here. I think it's just for aesthetics because hold on. Yeah, now it's -4 plus 1 gives you -3, but he still chose 0. So I think this 0 is basically the way clashes happen in this mathematical world. I don't think it holds
A 1,
that much meaning.
Yes, a 1 removes a 1, so gives 0. So he's 1
You can
that's
say so.
superior
You
than
can
his
say
one,
so.
and
Yes,
his 4,
you can say
yeah.
so. Yeah. Like a 1 and a -1 subtract each other and give you this 0.
Yeah.
Use it again and again.
0.
Okay.
Now pi over 4 is
Hold on.
Is 45 degree.
Takes
on
the
the
4,
unit
he
circle.
puts it there
Yes.
and jumps by pi over 4.
This is exactly 45 degrees.
Yes,
The
pi
arc is exactly
over 4, pi over 4 is 45 degrees. Now he's running on thin air. And by the way,
Imagine-
I have to take a moment here to say that the music is fabulous. Like this
Yeah.
is not
Nice
only
insight.
that the music, yeah, not only that the music is amazing, but it fits the video perfectly. Whoa, he uses I
So
because
wait.
I. Okay, let's come
Wow.
back. Look right there. Like when you draw the complex plane, you draw it like this. Like this is the real and this is the imaginary.
Yeah.
Correct. I give you 9 degrees.
Yes, you have a 1 here and an I here. So multiplying by I gives you a rotation by 90 degrees. You can
So
also wait. Okay.
So
What?
the plane he is in is the real numbers and imaginary numbers.
Yes,
perpendicular to each other.
this is the imaginary plane that they're playing in. And you can also see this
play
in
on.
polar coordinates or in the polar form by saying if I rotate by 90 degrees, which is pi over 2, this gives you cosine pi over 2 plus I sine over 2. Sorry, plus I sine pi over 2.
This gives I.
This is 0, this is 1, and this gives you back I.
Yeah.
So I is a rotation by pi over 2. And just to mention this quickly here, like using this form, if you have any complex number, like you can say z equals a plus bi, this can be written as a radius times a phase, e to the I of a phase, okay? So multiplying complex numbers basically means you multiply the radii and you add the angles. So by multiplying, because he's actually multiplying, when he did this, he multiplied. So by multiplying by e to the I pi, or by multiplying by I has a radius of 1 or a length of 1. So it doesn't actually
change his magnitude.
Yes, it doesn't change the magnitude, but it adds like
90 degrees, so he jumps 90 degrees.
Exactly. The vector from the origin you just add an angle of pi over 2, which makes him, rotate to pi over 2. Okay.
Okay.
Correct.
All right. Let's continue.
What is this ball?
Okay, it seems like this dot is like it creates a grid. I don't know. It's like a grapher. So he can use it to create shapes. Like this is the only thing I can deduce from this.
I think it's a dot that draws all the scales.
Yeah, it acts like a grapher. Like because he's gonna use it to graph a bunch of stuff.
Yes.
Uh,
And when
It's
he
like
goes in
it's
the
like a
when
Cartesian
he goes in
grapher
the
or something.
horizontal, when he goes in the horizontal, he gives
It's
real, and when
imaginary.
he goes. So this means
Yes,
the plane, the
this
black,
is,
is imaginary.
oh, look at this! Look at this! This is amazing. He draws the unit circle.
6
So
red.
it's 6
circle
red.
is-
So yes, what this shows, like when you try to measure the area of a circle of radius 1, the area is pi r squared, right?
yeah.
So it just gives you pi. Okay. So here, when he just created this shape of arc length 1, when you try to calculate the area here, like this is 1 rad. Hold on, we need to come up with a formula for the area of when you have an arc of a certain length or when you have a certain angle, you need to come up with.
I don't think
for the
he's
area.
talking about the area here. I think he's talking about circumference. Circumference 2 pi. So 1 pi is 3.15, which is a little bit lower than -1, and 2 pi is 6.
Oh, actually, you're right. I kind of messed this up. So yeah, we're actually here. He's talking about the circumference, but I got an illusion because he was, like the color of the internal of the area was different from the color in the outside.
It seems area, yeah.
Seems as if you're stuck in area. Yes,
correct.
It's an illusion. Okay, so yeah, then here when you try to calculate the arc length, it's basically theta times the radius. And the radius is 1, so the length is just theta. So moving here, you create an arc length of length 1, right?
Mm-hmm.
But the circumference of this circle is 2 pi. Okay, which is like approximately, you can say this is 6.14 becomes 28. Okay, so this is approximately 6.28. So by repeating this arc multiple times, he was able to barely get to the full circumference of this area at 6, which is just below 6.28.
Below 2 pi, correct.
Okay. Yeah.
Actually, 0.8.
Yeah. Okay. This arc is 1, so it should be the same as the radius. Okay.
He took an arc with him.
He then expanded the circle.
Yes.
This is the formula.
Now he sees 5.
This is the formula for the arc. Yes.
Yeah.
He increases the radius.
Decreases the radius. Now this is not a wait here. What he did here, he changed the circle to
Ellipse.
An ellipse.
Yes.
But there is not really any mathematical meaning behind it. He was just, playing with a theta symbol.
Messing around.
And again, we remember.
I think the arc equation can also work for the ellipse, correct? Or not?
No, I don't think so. No, I don't think so.
Mm.
So what was I saying? Oh, again, we have to remember here. He's again trying to find e to the I pi. Okay, so he's trying to figure out something new to find.
He's just playing with the arc now. He's just
but he's again trying to find e to the I pi.
Yeah. Want to try.
Okay.
Yes.
Shows the periodicity of angle. And then he makes this a division, and I don't really understand why he did this, but I don't think it matters because R is 1
Theta
anyway.
here is 0. Theta here is 0.
Yeah, but R is 1 anyway, so this is just theta, okay? So when he plays, whatever is happening right now, that is just theta.
Is dividing by 1, so it's just printing out the radians.
Yeah, exactly. This is just theta, and whatever is expressed here, this angle is 1.88 radians, and it keeps going like this. Now it's pi.
It's pi.
As you can see.
Now this will be good. Cosine and sine. Wait. We need to explain this. How pi got cosine and sine?
He split the pi into a cosine and sine. I actually
Does this
don't
have
know.
a mathematical meaning, or just plot and something?
I don't actually see how he split the pi into a cosine and sine, which is quite interesting. I think it's because pi is related to cosine and sine, but I don't see the formula because the first identity which comes to mind is the sine square plus cosine square equals 1, for example. I still don't see a pi here. So I think no, I don't see anything. I don't see how he made he split the pi into a sine and a cosine.
It's just for the plot.
Yeah, I think it's just the plot, and he wanted to make 2 hammers.
Now we need to address this.
Now this is interesting. We're gonna address it, but we gotta look at it first because it looks so cool.
That's true. That's true. Oh,
bro. He now switches both in the same direction. Okay.
we need to explain. We need to discuss this.
We gotta explain this. This comes back to what cosine, like what is cosine and what is sine. We know that the definition, like if you have a triangle, and this is a right triangle, by the way, and you have an angle here, the definition of the sine of this angle is this what we call the opposite, and this is what we call the hypotenuse, and this is the adjacent, okay? So the definition of the sine of this theta is equal to the opposite divided by the hypotenuse, right? And the the cosine of theta is the adjacent divided by the hypotenuse, right?
Correct.
Now, if you draw the unit circle, and we don't have to draw it, it's already there, so we're going to use it, okay? And you go make a certain angle, like if you go right there, make an angle theta, you can see right here that on the circle, the x-coordinate of this, because this makes a right triangle, so the x-coordinate of this, you'd say, like, this is 1. And correct. Yes, this is 1. So when you divide the x-coordinate by 1, you get the cosine, right?
Correct.
So the x-coordinate divided by 1 gives you cosine theta. And the y-coordinate divided by 1 gives you the sine of theta. Right?
This was the equations above, yeah.
Okay. So what he did here, he wanted to visualize, sine in terms of the unit circle. So what he did was that he made theta a function of time. So the angle just increases uniformly and keeps rotating and rotating, right?
So it gives us a sine wave, a cosine wave.
Yes, and he draws the axis. Like, we need to come back here.
Wait, so what he did here is cosine. He hit it with a sine.
Yeah, he hits it with the sine, okay? And he makes the time axis keep moving, right?
So the equation if we wrote it,
look, there's let's try to do it in an easier way.
T.
Hold on. Let's try to do it in an easier way. Okay. So what we have explained is that y is equal to sine of theta, right? Right.
Okay.
So what we said is that y is equal to sine of theta. So the projection. This means that the projection of this vector, whether it rotates with time or not, its projection is going to give you the sine of theta. So he rotates the angle with time. He rotates this vector with time. And the projection should give you the graph of the sine as you graph it with time.
Yeah,
It's actually better explained in his animation than what I'm saying. Like, whoever look at the animation, it would be much easier to understand what I'm saying if you look at the animation.
Yes, we have the triangle like this.
But
we have this is
whenever I try to explain this to somebody, I just show him this graph.
Yeah.
This is sine.
And this is what is fascinating about complex numbers. It can generate sines and cosines with the clicking of your fingers.
This is this. This will be this.
Yes.
This is sine.
So if the angle is equal to time, then y would be equal to sine of the time.
Yeah.
And then when you graph this, you would get this shape. So what he did is he graphed it, but he graphed it in a very cool way. He graphed it with an animation.
Yes.
Okay.
He just made it to you.
Yes. Okay.
Let's continue the video.
So you can see the projection.
Now cosine.
Cosine is the projection over x.
And we can also see the pi's where the shifting happens. Pi to pi.
Exactly. You can see that cosine of 2 pi is 1. And cosine of pi over 2 is 0. And cosine of pi is minus 1.
Yeah.
Correct.
Now he does both.
Now this is the equation is y equal sine t and x equals cosine t.
Exactly.
When he goes an I.
Now when he puts an I, he rotates like
from real to imaginary, but there is a shift.
Yes, of course there is a shift because cosine and sine are not. They don't have the same phase.
They are by over 2 shifted.
Yes, there's a shift of pi over 2.
Yeah.
So what he did when he multiplied by I is that he transformed it from the x-axis to the y-axis because the y-axis is the imaginary and the x-axis is the real one.
Yeah. Okay.
And it looks cool. So this is all we need.
Yes, we are over engineering because of the coolness.
Yeah.
Like, okay.
Yeah, okay. Come on, guy.
We're back.
Why? Because E is equal cosine. That's a nice sword fight.
Okay,
wait here.
Okay.
We need to explain this. We need to give a reaction to this.
This is actually, you can say this
What
in
is
two
this?
things. You can actually say that this is the definition of exponential, or you can say that this is the Taylor series of the exponential. So in this case, if we assume that e to the power x can be written, okay, if we assume that e to the power x can be written as a power, well, this is what we call a power series, which is the sum from n equals 0 to infinity of an times x to the power n.
Yeah.
Right there, if you plug in x equals 0, you get a0. Okay, so a0 is, let's call this f of x. It's just f of 0, right?
Which is 0.
No, it's just 1 in this case.
Oh yeah, 0 over n.
E to the power 0 is 1. Okay,
Yeah.
so if you take the derivative, in this case, if you take the derivative, like this is basic calculus, you just use the power rule. You just drop the n and then subtract 1. So the derivative at 0, this is equal. This equals the summation from n equals 0 to infinity, an times n x n minus 1.
But why did you take the derivative of the f of x?
You will see. Okay.
Okay.
So if you plug in x equals 0 now, you will get something interesting. If you this sum goes from 0, you just plug in n equals 0, this vanishes. So this actually is a sum starting from 1. If you plug in n equals 1, this gets you x to the power 0, which is just 1, right? So this just gives you a 1.
Okay.
So the reason why I'm doing this is that I'm getting these coefficients. Like what is a1, what is a2? How do we expand the exponential in terms of a power series?
Yeah.
Okay. So if you do the second derivative, what you will actually get here is that you will get 2a2. If you do the third derivative, you will get 6a3. And
so you get each coefficient?
You get the coefficient multiplied by something, and you're already able to see what this something is.
1,
This
2,
is
6.
the factorial of 3 times a3. Right?
1 factorial is 1.
Factorial is 2.
2
3
factorial is 2,
3
exactly.
factorial, 3 to 1.
And 0 factorial is also 1. So
Yeah.
we're not dividing by anything here. So we're not multiplying by anything. So what this tells you is that an is actually equal to, and you take, this is the notation for what we call the nth derivative, like an easier notation to do it, and you apply this at 0, and you divide this by n factorial. Right?
Right.
But there is something quite interesting about e to the power x, is that no matter how many times you differentiate it, you get it back.
Yeah.
So plugging in 0 in every derivative will just give you 1 in every derivative. So this term goes away, and you're just down with the factorial. So this just gives you n equals 0 to infinity of x to the power n divided by n factorial. This is the expansion of the exponential in terms of power
This is Taylor
series.
expansion.
Yes, this is a Taylor expansion. And what you do here is that you plug in I pi here, because this expansion actually works even in complex numbers. So you just plug in I pi here, and this will give you this, because you replace this x with I pi. So this is equal to e to the I pi, which is equal to -1.
Which is very interesting and very cool.
Okay,
Okay.
let's go. Yeah. Look at this. Look at this. He is
Throwing the terms.
every time he shoots a term, the summation starts from the one above it.
Yeah.
So
he finished. He released the first term, right?
Yeah, he released it because this is how it works. If you use the summation from n equal to 0 to some number of, like, let's say an.
It was just a series.
This is equal to a0 plus the summation n equals 1 to n.
Right.
And you just keep.
So he's just subtracting. He's subtracting it and shoot it on the animation.
Yes. He just splits it in this way and then shoots this.
Yes.
And he keeps doing it over and over again. This is an n, but this is infinity, so he can shoot forever. Okay.
Yes.
So he has infinite ammo.
Yeah.
And here, this is
now,
I pi to the power 0 divided by 0 factorial. This is 1. This gives you 1, right?
Okay, now this
This is
I
pi
over 1
divided by 1. So this should give you I times pi.
Yeah.
It gives you I times pi, yes? So it gives you have pi here, 3.14159.
But there is no I.
Yeah, I actually don't see where the I went. This is interesting. This is a nice remark.
I think it's just shooting the magnitude. Maybe because it's a real number.
Because this is to the power 1, so the I should have been here. Maybe the I fell, basically. Maybe it fell.
Or just giving him the magnitude. Just giving the magnitude.
Yeah, maybe the explosion happens proportionate to the magnitude. Again, we're overthinking this, okay?
Yes.
Guys, this is a battle. Everything is possible.
Okay, so here we get...
Wait, here becomes a minus.
There is a negative.
It became a minus.
It becomes a minus because I think he took a square, and the square of an I is -1.
So where is the previous I?
So he actually... Yes. Hold on.
1, 2
No,
is...
the two ran away. Oh, sorry.
minus
This
I.
gives you minus I. So I guess it's what you said. He's getting
The
the
magnitude.
magnitude. Yeah, I think you're right. Okay. Takes a pi. Hold on. What did you do?
Make the video slower.
Yes. No, I'm not gonna make it slower. Okay. Yes. So he multiplies. He multiplies the quarter of. Was this a quarter? I think that this was 1.
This is a quarter.
But we don't. But I don't think we do. I don't think we have to think about this too much. He just multiplies 4. Yes, he multiplies 4 by one one
Four.
quarter. So he made it into a circle. And then he added pi, which is the area. Pi, which is the area of the unit circle, to make it solid.
Yeah, he computed the area. Correct.
Okay. And then he multiplies times 8.
Wait. He does not multiply by 8. Wait, go back.
Okay.
He's multiplying. Make it slower. Slower so we can. He multiplied with 8 with.
With the height. 8 times the height.
Yes, so we make it slender.
Yeah, you're absolutely right. I actually didn't see it. That was very cool. And I don't want to slow it because it actually looks cool because it's fast. Like this video.
We go back and forth a lot. Yeah.
It looks because it's fast.
Wait, what happened here?
He just put the R aside and subtracted himself, and he is -1. So minus gives you a plus. So this is R plus theta. We need to remember that at the end of the day, e to the I pi is still -1. I know here it looks like a dog, but it's still -1. Okay. Okay. Increases theta. So he's basically.
This is smart. This is very smart. He's adding his
himself to the radius. Yes.
So he's expanding it. This is smart.
Yes, he's expanding it. Because actually, if you graph something like this, like if you graph R equals theta, you would actually see that I mean, in general, if you have theta increasing, if you have your radius increasing proportional to theta, you would see a spiral out. So he's
if you are graphing it 3D, not in 2D.
No, just 2D, just in polar coordinates.
If it's a function in theta.
Yes. At 0, it will just be at the origin, and as you increase, it will just keep spiraling out and out and out and down. Yes.
Wait, he divides by 8
to bring it back.
Yeah. What did happen here?
He just brought 7, which looks like a knife. So here he
flipped himself
by negative.
It was minus, so you flipped himself.
The summation again.
Taylor expansion again. What happened here?
Wow! I don't think anything happened. That looks like he just
sine.
He just used the dot, which is a grapher, as we explained before, to graph sine.
Yes. This is sine.
Brings out a 9. Okay.
Now we need to expand. We need to
this is actually very easy to explain. This is basically the remember the Euler formula, which is cosine theta plus I sine theta. And if you plug in minus theta here, minus I theta, you would get cosine theta because this is even. And if you put a minus inside cosine, it just gives you back cosine. But you would get minus I sine theta.
Yes.
So if you add the two, this cancels and you get 2 cosine. So you get the cosine is equal to basically this. You don't need to write it again. But instead of this pi, you have theta. And if you subtract the 2, you get 2I sine theta. So you have to divide by 2I and get this.
Yes.
So this is sine pi.
Yeah.
And this is cosine pi. There is one thing here. There's one thing here that we need to note. But it is still correct. If we go back here, this is an I sine pi, right?
Correct.
Yeah, correct.
So the sine is e to the I pi minus e to the minus I pi divided by 2i. So the I should multiply, and you shouldn't have an imaginary at all. Like here, there should be an I, and this I should cancel with this I, right?
Right.
This is wrong. So this is made an incorrect.
It is again not wrong because this is 0.
Ah.
This sine pi is 0. Because actually, e to the I pi is equal to e to the minus I pi. So if you remove this, you're basically subtracting something from itself. This is 0.
So 0, so it doesn't actually count.
Okay, and this gives you the minus 1.
He's just expanding himself.
Yes.
Expand again and again and again.
Now he adds sine pi over cosine pi, but he changes the pi into this dot, which in this case we said before that it functions like a grapher. Yes, but we can also look at it in mathematics. If you have a sequence like this, you can say A1 is the first element and A2 is the second element, right? But if you want to suppress this index but say that it's still there, you can say this is A dot. So this means that anything can go in here.
Any set.
That's an input field. Yeah, a field when you can put an input in it.
Yeah, basically the input can be anything. But I will tell you how he used it here, according to what I understand. I could be wrong, but I think how he used it here, turned it into a 10, and then he black boxed it into a function. Like he turned it into just one abstract function, which has the 10 inside.
Which is 9 multiplied by the magnitude of...
yes, and now he uses... Yeah, here...
Yeah, he gets 10. This is 10.
Yes, I think what I understand... It is a 10, yeah, it is a 10. But if you realize every one of those 10s, like if you look here... Here... You can see that there is only one 10, like one graph of 10 with every dot. So it's like, the way I understand it here is that it is just one period. Every point of those acts as one period of 10.
Okay.
One period of 10, or if we grab the 10, it's just one part of it?
It's just one period, which is like the period of 10 is pi. So it's just, you know...
Why when it hit an EI pi, it gives 0. It gives you, it vanishes it.
No, I'm not sure. I think it's just, you know, he's just shooting bullets, basically. But it gives you...
White kills, that's what I'm asking. It gives 0.
This is why I'm not sure. But what I see here is also one other thing, which is I'm not sure of.
Circle.
Is that this graph, which shows... This graph actually... this graph is something. This is something that you can... Like, this is something that you can graph and write a formula for, is that if you put these axes here and you say, I'm going to start at 0, hold on. So what I want is that right here at theta equals 0, yeah, this is the graph of cosine. This is r equals cosine theta. Because as you plug in theta equals 0, you just get here 1. And as you go to pi over 2, the radius vanishes. So this actually becomes something like this. But this doesn't look like this. This is supposed to be tangential, but you know, my drawing is bad. Okay? So this is actually the graph, the polar graph of cosine theta.
So just to make it...
it's just to make it...
It's just tan of theta multiplied with EI by generates us cosine theta? Am I getting something wrong here?
No. I don't think there is any mathematical meaning behind it. I think it's just, you know, explosions.
I don't want to believe this.
Yeah, I don't see, because then no, this doesn't look right. So
maybe something we are missing.
We are over engineering this problem.
Yeah. I think when it comes to collisions in general, he doesn't do math behind it. You know, like he either uses 0.
No,
or
I think he used it. I think when he multiplied himself, I think he multiplied 3 by 4 or numbers, and he got correct?
Yeah, but this is
Mathematical
different.
results.
Like whenever he uses bullets and swords, it doesn't really look like he's making something behind it. I think this is just because here it's just giving you the graph of cosine, right? But if you just move forward a bit, you get 0.
E to the I of pi is 1, correct?
Get another 0 here. E
E
to the
of
I
I
pi is -1.
is -1.
-1 multiplied by 10 is nothing. It gives us
It is just -10. Hold on.
minus
I
10.
think I know. If this tan was tan pi, what is tan? But tan pi is 0 though.
So
Yeah,
0
tan pi is
multiplied by
0.
-1 gives 0. Gives 0, so
All
it's
right,
correct.
all right. I guess that makes sense. But this would conflict with the fact that he's shooting the entire graph of the function, but yeah, you can say that because when but here he replaced the pi with a dot, so no. Yeah, no. But you can see it that way. I think we're overthinking this because this part exactly. Whenever it comes to collisions, he doesn't really add something to it. It doesn't seem like the part where you should be looking. You know what I'm trying to say? There will be other parts where we should be looking.
Guys.
I
We
think it's done by.
overthinking.
I think it's
It's
done
it.
by.
It's it.
I think it did not overlook this. I don't think it overlooked this.
Yes. Let's keep going.
Let's run it.
Hold on. How did he increase who increased the radius?
That's a very good question.
Yeah.
The radius kept increasing.
That doesn't make any sense.
I guess someone did. I don't
Wait,
know who.
pi r squared. This is the area. R is continue expanding.
This is because of e power pi I.
What?
This is
No,
because
I don't think E is expanding it. Maybe E is expanding it so it doesn't go out. Maybe.
Maybe. I don't know. Someone expanded it, but I don't know who. Okay, he connects the line, and then he puts pi.
This
Now
gives
he's
180.
Yes.
like an elevator. This is so cool.
Oh, this is like basically like aliens, aliens coming and he's shooting the aliens.
The movie robots, iRobots. Coming back, 180.
He shifts himself up.
Oh.
Now he puts the infinity.
Now he made the magnitude of tan infinite.
I think what it means by putting infinity here, like the way I understand it, is that first I told you that it was a graph of one period. Now it's the entire set. So shooting the whole tan altogether.
The whole period of 10.
Like from minus infinity to infinity.
Yeah.
And this is how I would explain this part, because it's like you multiply by an entire input set from minus infinity to infinity, and you get x, which can be anything from minus infinity to infinity. Let's call it x1. You multiply again, and you're multiplying the set of the real numbers by the set of the real numbers again, which gives you the square, which gives you pairs. And then you multiply again and again and again, and you get x3, and then you get x4. And then the set of all of these, like the set of all of these, would be R4.
Yeah.
Okay?
Now, how this weakens the outlier of the circle?
Not sure. You can make it however you want it, because I don't think there's an explanation. You can say that, he made the universe 4-dimensional because we live in a 4-dimensional universe, 3 for space and 1 for time, and then he got out of it, maybe. But this is just you and your imagination. There is no explanation here. Or maybe I could be wrong, but I would love for someone to correct me.
I would love the animator to comment on this video.
Okay, now this is the fun.
This is the fun part.
Yeah. This is the beast of this video.
Ooh. Bro.
The the integral.
This animation is crazy. This is insane. Okay, before we continue, like this animation is insane, but before we continue, we need to explain, because there is a lot to explain here, which I know that many people would, would overlook or would not notice. Okay, so right here, we know this. You just use the power
Taylor
series. We talked about this, yes. And then another one, this is Euler's formula. And this is just a sign again, but again, we talked about this. There was supposed to be an I, but we can, ignore this because this is equal to 0, right?
Right.
And then you have, you see these two, oh, wait, something here. Hold on. You would see this e to the I pi right there. There is no negative sign, but again, it doesn't matter because it's equal to 0 anyway. E to the I pi is equal to e to the minus I pi. You would see this here, right?
Mm-hmm.
Okay, you continue again, and this becomes that.
This is new.
Okay, so no, this is actually very easy. You plot this on the complex plane. This is the real, and this is the imaginary. And remember when I explained how do you multiply or divide complex numbers, right?
Yeah.
You have here 1, you have here -1, and you have here I, okay?
Mm-hmm.
1 minus I, hold on, this is 1 minus I. Okay, so let's put a minus I. Okay, so we graph 1 minus I, so it's 1 and it's minus I, so it gives you this vector. Okay, and we graph 1 plus I, which gives you this vector. Right?
Right.
So what we do here is that when you divide this by that, this means that you divide the magnitudes and you subtract the angle, right?
Okay.
So when you divide the magnitude, this is just a rotation of this, so it's just 1. The division is 1. But when you divide the angle, you're gonna have to subtract the angles. So subtracting the angles is basically the angle between these two. But not this angle, because we're subtracting this minus that. So it's actually going to be this angle.
Okay.
Okay? So this angle is pi over 4. And this angle is also pi over 4.
Negative pi over 4. Okay.
Okay? So what this angle is that there's pi over 4 from here and another one from here. So it's pi over 2. And we have a pi. So it's pi plus pi over 2. Okay? You take this. Yes, you take this. You put an I in here and an E, and this should be the division of them, right?
Okay.
So this is equal to I pi plus pi over 2 plus pi over 2 minus pi over 2. Right? And this is 2 pi. So this just vanishes and it gives you e to the minus I pi over 2, correct?
Correct.
And now you take this and you take the log, okay?
The log, this is the log or the len? Log, okay.
Okay, you take the log, okay? So when you take the log of this, you're supposed to get minus I pi over 2, right? Plus 2 pi I times some integer m.
I have a question.
Okay.
The log, you assume the log will cancel out the exponential?
Yeah. Isn't this what logs do?
But do you certain about this log? Is log not the log to the best?
The len.
This is a len?
No, no. Look, it's actually a convention that log is len. Like here, I am pretty sure that he's using the natural log.
The natural log. Okay.
Yeah,
Okay.
I'm pretty sure.
Yeah.
Because
Yeah.
actually, even if you use it in MATLAB, you can use log and it's just len, right?
Okay. Okay. This is for sure.
Okay.
Okay.
So, and it doesn't make any sense. Like this is all exponentials. Why would he get log base 10 here? It doesn't make any sense at all. So that's definitely the exponential log. Okay.
Okay.
And it gets you this, right? So this is gonna multiply the 2i squared, right?
Okay.
Okay. When it multiplies this part is a multiple of 2 pi, and it's gonna give you a minus I. So it's just gonna vanish. Like this part is gonna go away.
Okay.
This multiple of 2 pi. And this part, you get minus I times I squared, which gives you I. And you get this 2 cancels with this 2. So this becomes e to the I pi.
This is what we need to...
QED.
Okay? So
Okay.
there is one other problem here.
Oh.
If you do this, now this is a problem because this was an e to the I pi as well, right?
Should have given the same results.
Yeah, right? But look at this. What is I squared?
It's negative
Minus
1.
What is minus minus 1?
1.
Minus 1
Just
is 1.
Okay, so this just vanishes. So this is just e to the log of 1 minus I.
Correct.
Which is 1 minus I.
So this is a mistake.
So I wouldn't say a mistake because I would say that this is not math right now. He's basically making Megazord.
Maybe wait, maybe
that if
maybe
you're gonna talk about
the horizontal
about
and vertical, maybe the horizontal and vertical expansion is different.
could be.
Maybe
And also you can argue that the expansion of this line to here, because it actually was here. Like if you go back there, you would see that this line expanded, right? So it's now above the cosine. But I don't think it matters as well because at the end of the day, the whole thing should have given you minus 1, I suppose. Yeah, the whole thing should have given you minus 1. But if you evaluate this is minus 1, and this is plus 1 minus I. So this gives you minus I. And below...
It's cosine.
Hold on. Below you have cosine pi, which is minus 1. And you have...
2i.
Yeah, minus 1 plus 2i. So this is not minus 1. The division between the two is not minus 1. But it doesn't matter. Yeah, I think this is not math. Like what we're doing right now is just reshaping the stuff into something, okay? So what I'm gonna do is that...
I don't think he is also overlooked this. I think expanding in the vertical plane is different than expanding in the horizontal plane. That's
possible.
why he gives...
Possible.
Different.
But now look at what happens.
Limit x equal to infinity.
Yeah. When we come back to this part, it's like we have squished all the 10, like all the 10 graphs together. That as they get more compact and more compact, we're taking the limit to infinity, and as we reach infinity, it becomes an integral sign, and that is just for aesthetics. It just looks cool. Okay. And here there is actually a bunch of stuff to talk about. This actually looks very interesting. If you come here,
that's an integration from 0 to infinity.
We can evaluate. What are you trying?
Is there a relation between limits to infinity and the integral?
Yeah, there is, but I don't think this is what he used here, because the other relation is basically dividing the area under a curve. Like when you integrate, you have a curve, you divide the area under a curve to a bunch of rectangles, and then you sum them all up. And what you do here is that you take the limit as this width of a rectangle gets smaller and smaller and smaller. Yes,
infinity.
and the number of these
Rectangles.
rectangles goes to infinity.
Infinity.
So it just gives you the
Oh.
integral. Okay, but this is different from what he did, so this is why I didn't mention it.
Mohsen, this integral is like an expression for all tans from x
Oh,
to,
we
from
will
0.
get to this. We will get to this, but let's take it step by step because this picture here is a masterpiece. There is a lot going on. Okay.
Okay.
So first, let's take the arms. Then we're gonna take the body. Then we're gonna take the integral.
Okay.
Okay. So first, we speak about the arms. When you go to the arms, we have already evaluated this, and we know that it's -1, right?
Okay.
And this is multiplied by sine pi, which we know is 0. So the left arm is -1. Okay?
Okay.
The right arm, you have this. And this is, hold
The
on.
exponential expansion.
This is -1. This is an exponential expansion when you multiply I pi. So this is e to the I pi. So this is just -1. This -1 multiplies this -1, makes it a plus, and then cosine pi gives you another -1. So this makes this -1. And we have already evaluated this into being 1 minus I. And you get a -1. So this
Minus
is
I.
minus I. So the way I would look at this, is that,
One hand is real, one hand is imaginary.
okay, that works. And there's another thing that this is e to the I pi. And this is I e to the I pi.
And this is sick.
Okay? This is one thing. Now, the second thing is, when you go to the body, a bunch of, like, some people would say here, oh, he just made this robot or this, huge monster, like Dark Souls monsters. And these are just a bunch of symbols. But the funny thing is that actually this equation is true.
Interesting. Why?
Okay.
Interesting.
Okay. Like
How?
this is equal to this. We say e to the I pi is equal to the summation n goes from 0 to infinity. And here you have -1 to the n divided by 2n factorial. And then you have pi to the 2n. Right?
Okay.
And then you sum the summation. N goes from 0 to infinity. You get, again, -1 to the power n. And you get 2n plus 1 factorial.
This is sine and cosine.
Exactly. This is what I'm getting to. And then you get this. Okay, and then you would see here that he's dividing by 2's, and you would say these 2's are just the legs, right?
Mm-hmm.
So you have 2, 2, 2, 2. These are 5 2's. So you would say that here we're dividing by 1 over 2 and to the power 5. This is a 2 to the power 5, right?
Right.
So this is the expression of the body. And the question here is, are they equal? And the fun part is that they actually are, because this right there, this is sine pi, right? And it doesn't matter what you divide sine pi by, but you can even divide it by 2 to the power 1000. It doesn't matter. It's still 0, right? 0. So this part is all 0. And this is just cosine pi, which is -1. So this equation right there is true. Okay. So we have an e to the I pi here. We have an I e to the I pi here. And we have a true equation in the middle. And now to the crazy part, which is this integral. So okay. So you would think that this has no meaning, but take a look at this. You see these exponentials here, right?
Mm-hmm.
Okay. You'd see you see a bunch of stuff, and you would think this is just a bunch of random numbers, right?
Mm-hmm.
And this is what I thought in the beginning until I saw this, because why would you put 8 over 3 randomly? It doesn't make any sense, right? Like you could have made it 4, or you could have made it maybe 3. It looks better. Why would you have only one of them 8 over 3 and the rest integers? It looks weird, right?
Okay. After E3I.
Yeah, it just looks weird, and it gives you, you know, pause for thought. Something is happening. There's something inside that you don't see. And you would realize if you integrate all of these, something quite interesting. Let's integrate the first one. This is the integral from 0 to infinity, because the bounds are here, of 1 over 1 plus t squared dt, okay?
Correct.
That is just arctan. Arctan of, you can say, tau, maybe. And,
Okay.
and tau, you plug in
Infinity and 0.
Infinity and 0, correct? When you plug in 0 of an arctan, it just gives you 0. It's the inverse of tan, okay?
Yeah.
When you plug in infinity, what do you get?
Pi
You get pi over 2,
or pi over 2. Yeah. Yeah.
right? You see, like, do you see why we get pi over 2? Because if you actually plug in,
Pi over 2. Yeah, Mohsen.
if you plug in pi over 2, because if you plug in pi over 2 in tan, you get infinity, or you get, you know, the undefined part, right? Because you have a cosine below, and cosine pi over 2 is 0, and then you're dividing by 0, right?
Correct.
Okay, so when you know, in a sense, take the limit as you go to infinity, it just gives you pi over 2, right? You see this too, Rashad?
Mm-hmm.
You say this too? You see this too?
Mm-hmm.
You see this too?
No, don't say it. It's just, but
Okay. Take a look at this. The integral of sine t over t is also pi over 2.
But why no?
sine
But
square of t over t
Is
square.
also pi over 2.
I have a question. But
Sine
why
cube.
e to the power I e to the power 2I, not e to the power I? And this is so weird.
What?
Why the exponential e to the power I, e to the power 2I, not e to the power I?
I don't
As
think,
an,
I think he just puts a pattern here. He just puts exponential to the power a bunch of numbers, which are a sequence, times I, and you just try to figure out the relation between them, because I can see the relation. Like this, like I will tell you, I will type down the relation. If you take this exponential and you say this exponential is a sequence times I, then the final answer, the result of this integral, the integral of something, is going to be equal to pi over that sequence. If you use this equivalence here, you'll be able to see all the answers, because in this case, this is actually pi over 3.
but I have another question.
I think there is actually a more of a pattern here. I think e to the power the the lower part of the division actually has more it. I think he didn't only move from pi over, he didn't take the 2 from the denominator and just put it next to the I.
But this
I
is what I
think
see. I don't see anything else, to be
the
honest.
integration is not only for the function 1 over 1 plus t squared. I think it's for the function and it's multiplied maybe with e over e to the power I pi, or
I'm
for
not
the
I'm not sure
arms.
I'm not sure, because the way I see it here, the way I see it is that the integral of the function, the not the integral of the function. Like this exponential right here is the exponential, okay, of, and you put an I here, and then you have this sequence an, which is pi over the integral of the function. So this is the form which all of these take. It's e to the I pi. Oh,
There's a
There is
phase.
it's e to the I pi to the power 1 over the integral
what the
f of x. The fuck?
yeah, fuck yeah. What the fuck, dude?
I think that's what I'm talking about. I think there is more of a pattern here than what we actually thinking.
I don't see the relation between the 10, the infinite period 10, and this summation or this integral. Or
The what?
the relation between
No,
the
no, no,
10.
no, no, no. Forget about 10. We're not talking about 10. We're talking about the relation between this and whatever is corresponding to it. This and whatever is corresponding to it. This relation is this.
But
okay? That
but-
this right there, this is just e to the I pi,
Why is this? Why is this equation?
and then you get 1 over the integral of f of x dx. I'm not sure why, but this is what we have achieved, which is insane in itself.
Wait,
Because
to the power of
can-
1 over this means what? This means
like if you apply it here, to check again, this would give you 3 over pi, and when this multiplies, it gives you e to the power I times 3.
3i, correct.
Yes.
I'm asking
okay?
what this animation, how this animation results to this. That's what I think. I think it has a meaning. I think it has a meaning.
I don't actually see the meaning.
So
Okay, so we have actually figured out something new here. Okay, so this actually, like, whatever was written on the left was, like, you can type it in this form, which is e to the I pi all to the power 1 over the integral f of x dx, where this is the function. This is how what is on the left and on the right relate to each other. And you can do it, you can write it in an even more neat way. It's that this, like this e to the 2i, for example, is the square root, but not just a regular square root. It's the integral f of x square root of -1. Because this -1 is e to the I pi. And so this is exactly e to the I pi to the power of 1 over the integral f of x dx. This is insane. Like, this is literally insane. We're going to delete all of this and type this again, because this, I really like the look of this. Okay.
Wait, is this -1?
No, this is, you mean, yeah, like this is equal to this. This is what we have established before.
No, I mean the body, but the arms.
We said the arms, this was -1, and this was minus I think.
So -1 plus plus -1 plus -1 plus -i.
Okay,
No,
so
doesn't make sense.
So this was I pi, and this was I pi. So, you know, it's okay for me.
It doesn't give any.
It's okay for me. So here, what we have discovered is that you take one of these, and it can be written, like, in any of these rows, it can be written in this form, that like, let's say e to the 2i, this is equal to, we can type it in two ways. First, we can say this is e to the I pi to the power 1 over the integral of 1 over 1 plus t squared dt from 0 to infinity. We can also say that this is equal to the square root. We put a -1 here, the square root of -1. How can I erase? Okay, square root of -1, and, like, the base of the square root here would be the integral from 0 to infinity of 1 over 1 plus t squared dt. And this is another insane thing to say. So these two actually relate to each other. Every two of these relate to each other.
And it also relates to this. This is -1.
I mean, yeah, it does relate to this. This is why I wrote this one first, because this relates to e to the I pi, which is this. So yeah.
What you mean, Mohsen? We can find the continuous roots of -1 on the complex plane, or the roots in a.
It's not. Yeah. Look. You can define something like this. Like most of these crazy stuff, which you couldn't have done before, you can actually do them, provided that you now have the complex numbers in hand. Like the complex field allows you to do stuff like this.
This is
Okay.
insane. Okay. This is.
So this is
I think
quite
if
funny.
we go further, we'll find more insights. I think.
I think there could be more. I would encourage whoever watches this to look for more, and tell us if you find anything. This
write in the comments. Write in the comments,
yeah,
guys.
this is quite exciting. Okay, so now like because maybe this form is actually something that happened before, but we didn't know it. Like I don't know it, but someone else who was doing research on something, he came across this before. Okay.
Let's continue the video. We have paused for enough.
Before we continue the video, I'm just gonna type one thing, and we're gonna delete it. Okay. I'm just gonna type it once, and we're gonna delete it. Okay. For this, we already integrated. Okay. For this, I'm just gonna type a formula, and the integral from 0 to infinity, sine to the power nx divided by x to the power n. This is equal to pi over 2 to the power n minus 2k, n minus 1. And you can actually use this formula to figure out all of these. Like to figure out that this is pi over 2, this is pi over 2, this is 3 pi over 8, pi over 3, so on. You can use this formula to do it. All right, now we have done a very big pause. Now we can continue the video.
Okay.
Let's clear everything.
Without any pause, please.
And though there's gonna be one more pause at the end of the
There'll
video.
be a lot of pauses, believe me.
I like the scream, by the way, like the way he screamed.
What he's doing, he's actually making an area or something. He's actually very good insight.
It's
he's
not
integrating.
Area. Oh, that works. It could be integrating because
he's integrating the area. He's going to
area and integrating,
0.
or it just could be that it looks cool, and I can't even explain how cool this looks. Like I have repeated this scene. I have repeated this scene like 5 times because of how cool this looks. And yeah, look, hold on, look. If we go here, he's holding it from the 0. And then he flips it, like this is like Kung Fu stuff, and then he holds it from the infinity.
He's going in the vertical shift because of the imaginary field.
Yeah, this. If you take a look, because this is actually very interesting. If you take a look at this, there were 2's in here, right?
Yes.
If you evaluate this expression, this is -1. This is 1, so these cancel each other out, and then you get -2 e to the power I pi, which is 2.
I just expanded the 2 for ease.
Yes. Oh.
Now, what happened here? Does someone know?
It is stuff you already know. You already know
he used cosine plus I sine, so to make the helix.
Yeah, he just used both like he did before, and this dot, as we explained, it plots stuff, and he used the big circle as an amplification circle to the because he increased the radius. Yeah, he increased the radius, so it gave a bigger sine cosine.
And engineer.
again, it looks so fucking badass. It looks so good, and the fire. Look at this fire, man. Look at this fire.
Cosine plus I sine, as we said. Oh. His legs has been destroyed.
Oh, 100.
He's expanding our.
Oh. Damn, the animation looks so good.
Wait. I want to point something.
Okay.
Go back. The pi here, he combines the cosine sign to get a pi just to hold the trigger. This is amazing. This is just
Yeah.
very insightful.
He's holding it so it stays like this. It stays radiating, and then he spreads a bunch of numbers and an X. You can remember from the beginning of the video, he used X to speed up his legs. So now he's just gonna use this. He's gonna use
numbers.
this X to speed up this.
He's rolling.
Yes, he's gonna speed it up with these numbers and the X as a speed multiplier.
Yes. Boom. Even they put
I'm gonna have to take a moment to.
He put the sound of a motorcycle.
Yeah. I'm gonna have to take a moment to speak about this animation, like the fact that it looks like it's something ripping apart. It looks so good. This is one of the best scenes in this video.
Scenes. Yeah.
Yes, the animation looks so good. It looks like there's too much light, and I can't even explain how good this. I'm speechless.
Now we get the E and go.
We go to
now we are in the
imaginary
domain. The imaginary domain.
And you can see the real one on the other side.
Yeah.
I don't really see any insight behind the way these numbers are ordered.
Actually, I'm thinking about it. Is it really the imaginary domain? Because what we established that in the black domain, we had the real on the horizontal line and the imaginary on the vertical line. So maybe it's not the imaginary as it's
it is
complementary.
No,
maybe
it is because he multiplied by I, but he's just visualizing it in two different ways. Like whenever he wants to do it graphically, he just visualizes it as a rotation by 90 degrees. But whenever he wants to visualize it in the dramatic way, he pretends that he's going to another universe.
I think it's like the conjugate or...
No, I don't think it's a conjugate, because a conjugate is also, it's a reflection, so it can be expressed using graphs. But this is just, he moved into another dimension, like the imaginary dimension.
He changed it.
And the problem is the imaginary dimension was already there.
Yeah,
the imagination was in the real one. The vertical.
I think what Mohsen.
No, the other one was graphical. This one is like he went to the dimension. He literally went there.
I think what you are trying to say, he changes his domain from domain to imaginary domain. That's it.
Yeah, that's what I'm trying to say.
I think there is more to it. I don't know.
What I think there might be more to it is these numbers.
Now wait. Go back.
These numbers could have a pattern that I didn't notice because.
No, wait. Play the video.
I think
continue playing.
It becoming black means that the imaginary and real dimensions are collapsing into each other.
Wait.
He just
+5.
Yeah, he just
He's going in the real dimension, the horizontal. Correct. Continue.
I'm not sure if it's real, to be honest. I think he's just running.
He's going in the
he's the positive direction +5. The real number, the positive numbers are horizontal. The imaginary
I think
the positive imaginary numbers.
In this universe, after he went to the other domain, the real is the complex and the complex is the real.
No, because if it was this, he would go up. He's adding.
He would go up. He would go up in the other one. Yes, he is now living in this dimension, in which adding
the real addition goes right. Correct.
It goes right
in the original one.
Yes.
And here also, it's also adding real and going right.
Yes. But whenever he adds a +5, it implicitly it is a +5 times I. But you don't have to add the I because you're already on the axis, the horizontal axis. You're already in the imaginary domain.
Maybe. Okay, this makes sense if the imaginary and real here is flipped. The imaginary is horizontal.
This is what I'm trying to say. I didn't even think the animator thought about this part, but I think like if I would think about it, this is how I would see it.
Okay, he would be multiplying I now. Let's see this.
Yeah, so like the only thing, I gotta make this note, the only thing that I think might have a meaning, but I didn't see it, is these numbers. This could be like some sort of fractal or some graph that I didn't see before, or I didn't interact with before. So I don't know what it means, to be honest. If anyone knows what it means, please tell me in the comments.
Let's continue. It's like the sea. He was swimming like in a sea.
See, now he multiplies by I, and it brings him to the other dimension.
Now there's a lot of explanations that will happen now.
Oh. Hold on. We want to make a truce.
We will give commentary. We will give a commentary on this part.
No, I'm saying, hold on. Let's like what he's saying. He's like, hold on. Let's make.
We'll be commenting now. Yeah, we'll be commenting now.
Let's not fight. Okay, truce.
Okay.
I just want to go home. I don't know how to go home. Maybe if
so
I went through your door, I will go home.
No, I don't think this is this means door. It could mean door, by the way, because it looks like a door. But as someone who thinks in math in general, I think this means the multiplication operator. Like in math, whenever you want to multiply a sequence, like when you want to sum a sequence, you say sum like sum an
multiplication
n equals say 1 to maybe infinity or any number. When you want to multiply, you just use this symbol right there. And you say n equals say 1 to n. This means multiply
A0,
this.
A1, A2, yeah.
Yes, exactly. So I think what he's trying to explain is that he wants to multiply.
He
wants to multiply. We're gonna see that he wants to multiply I after.
I just think segment. It's a door. I think he made the animation of walking.
You can. But I think like you thought of it as an animation of walking. I thought of it as him counting the terms that he wants to multiply. It actually makes more sense as a walking animation, and that he's making a door. And I also understood it as if it was multiplication, and he wants to multiply terms. And the reason why I thought this,
I think for the last part of the video, correct?
No, because not the last part, just 2 seconds later.
Okay, let's see.
This.
Oh.
But I think actually that I think about it, it actually feels more, it makes more sense as a door and someone walking. It actually makes more sense. But I guess my brain thinks too much in math that it forgot the real world. Okay. Okay, so here, yes. It's like, stop, no. Wait, I want to explain something to you. It's like multiplying multiple i's, like if you have I and you
wait. I think your first explanation is correct. I think he is telling him if you multiply it i's multiple times, I will be able to find a door that would get me home. Because he already tried. Then tried the I.
Correct. Then both are correct. It's a door and it's multiplication. I like it.
But a multiplication n times because he's now sorry because
yes,
if you multiply it 4 times, nothing will happen.
1. If you multiply again by -1, you get -I, which is I to the power 3. And then finally, when you do it
4
once
times
more,
1,
you get I to the power 4 is 1. Yes. Okay.
So nothing can change. He's sad now.
I like how we're explaining how to multiply I after we just wrote some of the most complex equations in existence.
The curve of complexity is
okay. Let's keep going. It's like, wait, I have an idea.
The cool part.
I also have to praise the sound effects throughout the whole video. Apart from the music, the sound effects are, crazy.
Amazing.
Like this futuristic elevator sound effect is so amazing. And it also looks like he's dropping it in a time machine or something. He's like, yes, standing there. And there's something that I didn't talk about before, and it is that when he drew the unit circle back in the video, it actually had this exact same size. So even though he's not writing that this is r equals 1, we know from the comparison of sizes this is the unit circle. Okay.
Yeah.
The length of the animation is
He's like
basically
2. He's like 2.
Like
Two,
2.
yeah,
His
2.
length is about 2. Okay, like in this world.
2
Okay,
units.
so here he uses the Taylor expansion again, right?
No.
And
We
then
think
he
what
and
is
this is
what is the
yeah
denominator here?
what is this? Okay, so first of all, you would ask yourself, what is gamma? So gamma, the definition of gamma, which is called the gamma function because obviously, okay. So gamma, which is actually a function of a complex number, like in its most general form, is equal to the integral. And I actually need to remember, this was an integral from 0 to infinity, right? We're going to check that. I'm going to write it down, and then we're going to check it. I think it was t to the power
complex
of z minus 1. Hold on, I'm going to write it first, and then we're going to talk about this. Minus t dt. I'm not sure if I got this correctly, but I'm going to go check it. The gamma function is basically a generalization of the factorial. In complicated terms, you call it an analytic continuation of the factorial, okay? But please, we're not going to get into analytic continuation, okay? So we're just going to say it is a generalization of the factorial in the sense that, as we just saw there, when you take gamma
of integer,
you take gamma of n, okay? This is equal to n minus 1 factorial.
Okay,
So this is like, this is a special case of gamma. We wrote the factorial as a special case of gamma for integers, okay? So here we can see that before the switch, this was n factorial, right? So n factorial using this formula.
He took n out, and then
this becomes gamma of n plus 1.
Yeah.
Okay?
Correct, yes.
And then he puts a 2 and it does a change of variables.
He divised over 2 and
yeah, so he does a change of variables. This, like, if this counter counts from 1 to 2 to 3 to 4, this is not actually legit. It's not, because before the summation, like before he puts the 2, we were summing over integers. Now we're summing over
integers also.
Also integers. It might actually work. No, hold on. Look. I got it. It's sum over n being even. Okay, you sum over n being even in this formula. This is what he means.
So
because if you do it this way, 6, you start from 0, 0, and then you put 2, and then you put 4, and then it keeps going. As you do this,
but if you
gives you back the old summation.
Yes, okay, that's what to talk. Yes.
Because you're gonna put 2. This is gonna give you
2 over 2
here,
equal 1. 4 over
exactly,
2 equal 2.
1 here and 1 here. Yes, and then the summation stays the same. Okay.
Yes.
Brilliant. Okay, so we're gonna just erase this.
Let's continue.
We don't need that anymore. And then this keeps going.
So what he does now.
Okay, so here he keeps pressing equal, and then he gets a dot, and then he presses equal again, and then a bunch of crazy stuff happens, right?
What are those crazy stuff?
Okay, so we're gonna talk about what exactly are those crazy stuff. Okay, so as you would know, you have, like, whenever you're in one dimension, you can measure length. Like, you can measure the length of an interval, right? So if you make an interval like this from minus, let's say, r to r, in one dimension, this is actually a circle. It's a circle because what is the definition of the circle? The definition of a circle is all points in the space which are equidistant to an origin, and this distance is r. So in here, the only points that can do this
from 0 to 1 is 1, from 0 to minus 1 is 1. So
it is just 2 points that can do this here. So you can say that here, if you want to calculate the length of this circle, because this is a circle, it's like one-dimensional circle, it just gives you 2r, okay? And then as you go up, you can calculate higher and higher stuff like area, which is two-dimensional concept. And then you can calculate the area of a circle. As you go up slightly higher, you go 3 dimensions, you can calculate the volume of a sphere, right? Now, you can actually go higher. There is something called the n-sphere. We have already spoken about the n-cube. Now, there is something called the n-sphere. Like the n-sphere is that a 4-dimensional sphere is all points which are equidistant to an origin in 4 dimensions. And the same goes in 5 dimensions. And by saying equidistant, you say that the distance between whatever your point is and your origin gives you r. And distance changes based on your dimension. Like if you're in 2 dimensions, your distance would be, like, let's pretend that we're calculating distance from an origin, and the origin is 0. Then your distance would be x1 squared, the square root of x1 squared plus x2 squared, which is easy to see because this is the Pythagorean theorem. Okay, so this is just Pythagoras. You would do this, and you would have your x. This is x1, and this is x2, and then this squared plus this squared gives you this squared, and then you get this. Okay. In 3 dimensions, you would just add x3 squared here. Okay. You can keep going. In 4 dimensions, this would be like this, and then you keep going until x4. This is actually called the Euclidean distance. The Euclidean distance in an n-dimensional space. Okay, so you can define what is called a hypersphere, an n-dimensional hypersphere, right? Now, in order to measure the n-dimensional volume or the measure of this hypersphere, you would have to do an integral. And if it's an n-dimensional one, you're going to have to do like an n-integral. There is a double integral. There's a triple integral. You can do like a quartic integral. And if we have an n-sphere, in order to calculate the volume of this n-sphere, we're going to have to do an n-integral, like n integrals, everyone after the others, like integral, n times dv, which is the volume, which is the n-dimensional volume in this case. Okay? This integral is going to be much easier in the hyperspherical coordinates, because in hyperspherical coordinates, the equation of a hypersphere is radius equal constant, and this is it. This is the equation. So it's going to be very easy to integrate this. And after you do it, you're going to get a formula for the volume of a hypersphere, and the formula is this: the volume of an n-dimensional hypersphere is pi n over 2 divided by gamma n over 2 plus 1 times the radius to the power n. Okay, and just to make things familiar, we're going to use this to calculate a bunch of volumes. Like we're going to calculate the area of a circle. We can do this kind of stuff. Okay, so let's say we want to calculate the area of a circle. How would we do that? Here we would put the dimension equal to. So this would give you pi to the power of 1 times, this is going to be r squared. And here, when you put 2, you get gamma of 2. But gamma of 2 is 2 minus 1 factorial, which is 1. So it gives you pi r squared, which is the area of a circle, which is the volume in 2 dimensions, right?
Okay.
You can actually do the sphere. It's slightly more complicated, but it's doable. We can do it. In the sphere, it becomes pi 3 over 2. But hold on. Let me not write it 3 over 2. Let me write it as pi times the square root of pi, which is exactly the same as pi over to the power of 3 over 2. Okay? And then you would put r to the power 3. You would divide that by gamma
3.
of, no, 3 over 2 is 1.5. So it's gamma 2.5. So this puts us in a position where we actually need to use the gamma itself, because the factorial only works for integers, right? But you can actually calculate this with the help of like a bunch of simple information. Gamma of half equals the square root of pi. That's all you need to know. No, actually not all. There's one more thing that you need to know. And there is this recurrence relation that says a gamma of z plus 1 equals z times gamma of z. You use these two, we can get gamma of 2.5 because gamma of 1.5 is going to be equal to 1.5. You subtract 1, you get a half times gamma of a half. This gives you the square root of pi over 2. We're going to do the same thing again. Gamma of 2.5. This is equal to 1.5 times the square root of pi divided by 2, which is 3 over 4 times the square root of pi, right? Now, all we need to do is get this and plug it in here. As you plug it, the square root of pi will cancel out, and you would get pi r cubed. And this 3 over 4 will become 4 over 3. So you get 4 over 3 pi r cubed, which you can confirm is the volume of a sphere. And this formula goes on as you go up. This calculates the volume of an n-dimensional sphere. But you can see the similarity between these two, right? Like if we go slightly back in the video, before he plugs in anything, you can see pi n over 2, gamma n over 2 plus 1. This is actually the volume of a hypersphere, but there is a factor missing. Check this out. This is missing. But why though?
R equal 1.
Exactly. We have already spoke about this. This circle, comparable to his size, has radius 1. So as you plug in 1 here, this is your expression. So actually, e to the I pi removed the I and then expressed itself as an infinite sum over volumes of like n-dimensional hyperspheres, like hyperspheres from 0 dimension to an infinite dimension. And you can see in this video where the 0 dimension is. Like as you go here,
it's a point.
It gives a point. Yes, exactly. So this is a 0 dimensional.
0 dimensional.
Okay. And it keeps expanding. I don't know why when he moved to the next one it gave a circle. It should have given a line first because it's a one-dimensional sphere, but you know, he did all of this. We're not going to talk about this, okay? So he keeps increasing until he hits an infinitely dimensional sphere. So now he's covered in an n ball, not an n ball, an infinity ball. He's covered in
n-dimensional ball.
An
infinity dimensional ball, yes.
Yes, he's covered in an infinity ball. I don't even know if that's a thing. Okay. And then okay, we're gonna clear the screen now.
Yes.
And then
he goes to say bye.
They either say goodbye, and then he inputs the I. And here there are a bunch of theories like that we came up with. Okay. So talking about this, first, like if you go back for a while, they were talking about how they wanted to multiply a bunch of i's to get into an extra dimension that is different from the real one and the imaginary one, and it was impossible because of the periodicity of pi. So what the exponential did is that he covered him in a ball which was infinitely dimensional, and then he inputs the I into this ball, making him jump from this dimension into another dimension. It's also like an imaginary dimension, but this time, I don't know, it's like he weighted it by an infinitely many dimensions. So he went beyond infinity. He went into a dimension which is beyond infinity. Or you can think of it in a way that he just used, is like I is used like a portal. It's like it portals, okay? And first, it was just the basic portal, which just goes to the imaginary world. But now, as he inputs it here, it exhibits the properties of the infinitely dimensional ball and warps him into a dimension which is beyond this infinite dimension, which is supposedly his world. Like he's now coming back to his world, right?
I think the infinite dimension ball It's like the door, but it's a closed door. When he adds the I, he unlocks this door somehow.
I think, yeah, I acts as a door opener. Like whenever you put the I, like I is a symbol for moving between imaginary and real, so it opens dimensions. So when he
when he used it in
say,
the symbol term, when he used it in symbol, he just moved from the dimension he is in to the imaginary dimension and then come back.
yes, but now
What he
he
did,
actually
made it
enhances
infinity. No, he made it an infinite dimension, which encompasses all the dimensions of the reality he is in now. Then he added the I, so
I agree with
flipped
this.
to the infinity in dimension, which is the real dimension that he's in, the real world he's in.
I think I agree with this. I think like if this was a two-dimensional ball, then he would move to a third dimension above the imaginary one. If it was a 3-1, he would move to a fourth one. And it keeps going and going and going. Now, as he inputs it beyond infinity, it makes him jump beyond infinitely many dimensions.
I know.
Which puts him.
I don't think it's about infinity. I think it's about moving. Yeah, when he used the I in simple terms in the first of the video,
I think it's about going beyond infinity.
I'll tell you what I think. I think when he used the I in the start of the video, he moved from the 2D dimensions that he's in, from the real to imaginary. Okay, but he's also 2D, from the 2D real dimension to the 2D imaginary dimension. What he did here, he made an infinite dimension, not 2D dimension, infinite dimension. Okay, that encompasses all the information, all the dimensions.
This is not an infinite dimension. This is infinitely many dimensions, because a hypersphere is a sphere in more like an n sphere is a sphere.
It encompasses all dimensions.
Hold on, take a look at
infinity dimensions.
Take a look at this. This is how I see it. Like you have a plane here, right?
Okay.
This plane has the real axis and the imaginary axis.
Correct.
Right? So as he adds an extra dimension to the ball, then inputs the I warps him to another one which is perpendicular to both of them. As he increases one more dimension, the I warps him into a dimension which is perpendicular to all of these in a four-dimensional space.
Wait. So when they both go through the door with one I, he did not go to another 2D dimension. He was
still in this plane. He was still in this plane.
As you were talking, he added an I. He made an I, so he must go on third dimension.
As you were talking before, like you said, how did he jump to another reality when he could graph them in 2 dimensions? You're right. He did jump into another reality, but the complex number is still in one plane. It's the complex plane. This is what we have been graphing everything in. So as he
what does I do? What does I do?
Just moves you from here to here.
That's it?
Yeah. But here, in this context, it has a different meaning, which is not mathematical. It has nothing to do with math. In my opinion, maybe there is more to it that I don't know. Maybe there is math that I don't know, or maybe it just doesn't have that many meaning. You just get the meaning from context. So the meaning that I got is that you enhance the dimensionality of the complex plane using the hypersphere. So as you add, like, let's say, if as you put a one-dimensional hypersphere, you would probably get the real thing back. As you added 2-dimensional, you would be able to jump over the imaginary one. As you add 3 dimensions, you can jump into one which is perpendicular to both of them. As you add 4 dimensions, you go something perpendicular to all of those, and you keep going over and over and over and over again. And so when he inputs I after he reaches infinity, he warps into a dimension which is orthogonal to all of those infinitely many dimensions below it. So it's as if he's...
I got this.
Yeah, it's as if this mathematical world has a number of dimensions, which is equal to the integers, right? Like there is the 0 dimension, 1 dimension, 2 dimension, 3 dimension, 4. Yes, the natural numbers. Yes, you're right. 5, and then it keeps going. Okay, and like every dimension in this world is one of these. So no matter where you go, as long as you're in one of these dimensions, you're still stuck in here, and you want to jump out of it. And the way you would jump out of it is that you want something which is beyond infinity, which you can say, for example, is like if you go to the topic of ordinal numbers, we can say it's omega. Omega is known to be a number which is bigger than all of the integers, like all of them. Like going to omega would be a way to jump out of the integers. So what he did here was that he made him jump orthogonally out, like in an orthogonal direction out, which is orthogonal to all these dimensions. So he went out of this mathematical world entirely. So he's here now, and this can warp him to another reality. This is the way I think of it in my head. Not sure if it's right though. I would love a confirmation if the animator saw this video.
I need
I got the headache.
Oh, yeah. I need a clarification. One clarification. What do you mean? What hypersphere formula did? It stacks many infinite dimension of spheres.
Okay, I'm gonna have to stop you here. I don't think it stacked many of them for a reason, because when you go back here,
just added them. But stack, just addition.
Yes, I actually thought about this. Here, you got 0, and then when you did this, the dot vanished, and then when you did this, and then we did this, it's just one sphere, as you can see, but it's just increasing in dimension. So I think
but this is an addition.
It is an addition, but all he's doing is that he's taking from this addition and throwing it on him, and I think it's replacing the other one for no reason that I understand. I don't know why, but this is visually
not a stacking, but replacing.
Yes, it visually looks like he's replacing them, not stacking them. This is what it looks visually.
But replacing them, okay, it replaced every hypersphere by another.
So now he's covered in one hypersphere that is infinitely dimensional.
It replaces it replaces the lower dimensional hypersphere by higher dimensional hypersphere until it reaches infinity, infinite dimension hypersphere. Then the eye project or take them to an perpendicular world to this hypersphere.
I think of it this way. There is no mathematical confirmation for this, but I just think of it this way. It looks like this works.
But why? But the eye is just an eye key, or it's just a key for a door.
Yeah, it's a key. It's a key for a door which is perpendicular to the plane in which you're in.
Okay, like, it's a key for a door.
Like if you are on the real axis and you input I, it puts you orthogonal to it. So it's a key to a door.
Okay.
Orthogonal.
All right. Yeah. What do you mean? What do you mean?
But you need to specify the dimensionality in which you want to jump. So in this case, and by the way, to everyone hearing us and trying to think about this conversation, this is not mathematical at all. If you multiply by I twice, you just come back to the real. Okay, so this is just us being. Yeah, we're just going into the interstellar universe, and we're doing some we're doing some drama. There is no real math to this. Okay.
Some drama. Okay.
Okay. Okay. There is no real math to this.
I think if there is real math to it, I think it will be he is trying to.
It would be weird. It would be weird if there's a real math to it, because here, as you plug in I, you can factor this out. It gives you I to the power infinity. What the hell is this? And it's multiplied by this now. So I don't even know what this is. So I can't even, I
think about it.
Yeah, this is undefined.
Maybe that's
why.
This
is impossible.
No,
this is impossible.
Maybe why
this could be an explanation. It could be an explanation.
Yes, maybe this is why he used it. He wanted him to go to the undefined reality that he does not comprehend, which is the real world.
Okay, it could be that it could be that he created a sum and he made the sum go to infinity. Like he made the counter hit infinity first, then he plugged in the I so that he doesn't have to take the limit, because if he takes the limit, then it actually doesn't go anywhere. It just keeps repeating. But here he didn't take the limit. He just plugged in like an I to the power of an actual infinity, not a potential. Like a potential infinity is a limit infinity. Wait. An actual infinity is like the infinity itself. Okay, what do you want to say?
It is funny. It's funny though. The world of Stickman is a stick world. Yeah, it's an imaginary one. I think it's
Yeah,
portaling.
but you know, we can
It port.
argue. Hold on a minute. We can argue that the word imaginary is actually a misnomer because imaginary numbers are not imaginary. They're actually just they're just as real as the real numbers.
Yeah.
Yeah, they're every bit as real as the real numbers.
Maybe Karim's perspective is an interesting one.
It could be,
a good
but
one.
I think like actually
The imaginary number, when he plays with Alan, he plays with him on the real world, on the computer, with animation, all this. It's actually the real world. So what he tried to do is to move from imaginary world to the real world.
If this was the case, then he could have just multiplied himself by I and went out of here.
And I tried this, it didn't work. So I think that
no.
the counter is trying to.
It portals the idea, the Euler formula from real world to imaginary world by multiplying by I.
But wait,
look,
he moved, but in the same dimension. So this is why he didn't get out. So when he did the hypersphere, the infinite dimension hypersphere, he went out of this constrained dimension to the real world.
But the meaning is not can I speak?
Yeah.
The meaning is still not attached to the I on its own though, because the I itself, when it multiplied something, it just moved it inside this place. Okay, but here we needed to add something from outside, which is the sphere. So the I itself doesn't possess this meaning on its own.
I think
I really hope
the
animator
I think
comment on this video.
I think it is a multiverse theory. we hear in the verse.
It is sort of a multiverse, but not a multiverse. It's like a multidimensional theory. It's like when you speak about string theory, you say there's 11 dimensions, right?
Yeah.
Here we're saying there is infinitely many dimensions, and we even want to go further beyond infinity to get out of this world. So we kind of broke the entire theory.
Yeah. Here we are in the dimension of mathematical equations, and
exactly.
we are go beyond, go to the world.
And we're saying that the cardinality of this dimension of mathematical equations is aleph null, right? We're saying that it has the exact same size of the integers, and we want to move out of it, right?
You're right. I'm totally with you. I'm totally with you, but I think we are going.
I think we have paused enough.
Yeah, I think so as well.
1 minute, please. What I'm thinking about, what I am thinking about right now, this is a dimension of mathematical equations, and we want to going out, or the stickman wants to go to his home, the stick world, or the stick world.
That's true. That is true.
And he used or the Euler formula helps him by the hypersphere formula, using an hypersphere formula to encompass him inside, and then put the I as a key lock, as a key as a key for the door to portal him from, or to take him from this world to this world. This is what I see.
Sure. And we're, it's like the key has a specific weight, and it's weighted by the dimensionality of the hypersphere.
This is a string theory, a new string theory here in this video.
Okay, so the dimension of the hypersphere, as it goes on, it attaches to different vectors. Like you go up and it attaches to this, you go up, attaches to this, you go up, attaches to something else perpendicular to this, maybe perpendicular to the screen, and it keeps going and going and going until it goes beyond the infinity, which is the ordinal number omega, maybe, possibly, or could be anything else. And that's basically the theory that we came up with in this, part. This is what came to mind. I don't know what the animator meant. I would love to know what he meant. If
Welcome
you
to
tell us.
String theory. Mohsen string theory.
Okay, I would love for the animator to tell us if he sees this video, if he ever sees this video. Okay, so we continue.
Okay, let's
Okay.
continue.
We've spoken for enough. This is like a sign of peace. Like the war has ended, and now his family comes back to him, and this is an emotional moment.
Can you comment about
These
the
are just
names
a
of
bunch
this?
of just a bunch of symbols. Like this is
The names.
zeta, which is famous for the Riemann zeta function. Like whenever someone says zeta, the first thing that comes to mind is the Riemann zeta function and the Riemann hypothesis. This is delta. In mathematics by convention, usually used for a very small, like a very small quantity. Phi, usually used for angles.
And the
And we've
background.
got the big guy right there. Yeah, this is Aleph, which we just talked about in like a minute before. Hold on. Aleph, if you add a null here, this is actually the symbol used for the cardinality. And by cardinality, we mean the size. This is used for the size of the integers or the natural numbers. Like the integers, the natural numbers, or anything that we call, countable, it has this as a cardinality. There is nuances
That's why
to
it's
it, but let's
huge.
just there's nuances to it, but let's just say the integers are the same size as the natural numbers, and the size of both is aleph null, which is this is aleph and this is null. Null means 0. Okay.
Yeah.
And they all lived happily ever after. The end.
The plus end.
Yeah.
Okay.
Yeah.
And
That
that's
was
it.
beautiful. That was beautiful.
This was the
That
longest reaction to a
we're
video.
gonna have to take a moment to praise this. This is one of like I'm used to this because I've been
Your
watching
work.
Alan Becker's videos since I was a child, and I remember that I used to show it to my friends in school on the phone. Like his early videos, like the Animator versus Animation, the original one, and the Animator versus Animation 2, and the third one, which was about the Chosen One. And by like back then, the Animator versus Animation 4 didn't come out yet. It was only the first 3. I was showing it to all of my friends almost everywhere. So, I've been watching him since long, and actually his videos are masterpieces. But this one
This is on a whole new level.
yeah, this is on another level. Yeah, so I would like to, thank Alan Becker and specifically his animator who made this work, who made this video for this amazing work. And I would love to see more if you plan to do more about math. Like this was amazing. Thank you for this video.
And we can end it here. Thanks for everyone who continues the video till the end. We hope you all guys has enjoyed it. And if you have any comments, any questions, or you have noticed something we did not notice in the video, please put on the
If you have
comment.
if you have
whatever.
any comments, you can comment, obviously.
Obviously, yes.
It's a comment.
Thank
This is what
you.
it's called.
Oh,
Thank
yeah.
Thank you.
thank
Thank you
you
very
Thank
much.
and
you and
peace.
goodbye.